Hi and welcome back. Previously, you learned how to compute double integrals over type 1 and type 2 regions. Consider the region in between two semicircles in the upper half plane as given on the slide. It is a region of type 1, but it is quite hard to properly describe it as a type 1 region. We want to somehow exploit the circular symmetries you see in this region in order to make this description less complicated. It turns out that switching to so-called polar coordinates will greatly simplify how we can describe this region. Normally, you describe points in the xy plane by means of the x and the y coordinate. Instead, you can also describe a point by two other coordinates, r and theta, which are known as the polar coordinates. The radius r is defined as the distance from the point to the origin. In a formula, this means that r is the square root of x squared plus y squared. In addition, the angle theta is the angle between the point and the positive x-axis. As it is an angle, theta is defined uniquely up to integer multiples of 2 pi. Usually, theta is taken in either the interval from minus pi to pi or in the interval from 0 to 2 pi. It is impossible to express theta in a single formula of x and y, so it's usually better to draw a picture. Reversely, x and y can always be expressed in terms of r and theta by the formulas x equals r times the cosine of theta and y equals r times the sine of theta. Describing regions in polar coordinates is usually easier than regular coordinates when the region possesses some circular symmetry. On the other hand, for regions such as rectangles and triangles, regular coordinates usually remain the optimal choice. For instance, consider the region we discussed previously. In polar coordinates, this region can be described easily by noting that the radius r changes from the inner circle with radius 1 to the outer circle with radius 4. In addition, the angle theta starts at the positive x-axis, where theta is 0, and ends at the negative x-axis, where theta is pi. Since you have now seen how to describe regions in polar coordinates, let's see if we can also use them for computing double integrals. Consider the following region R. This is an example of a so-called polar rectangle, since the radius r ranges between the fixed values 1 and 5 and the angle theta between the fixed values 0 and pi over 2. In order to express a double integral over this region as an iterated integral in polar coordinates, we will take a look at the corresponding Riemann sum. We subdivide the region R in smaller polar rectangles. In each small polar rectangle, we choose a point and compute the function value there. We can then approximate the double integral by the sum of the volumes of the bars you see on the picture on the screen. This approximation is called the corresponding Riemann sum. Here you see the Riemann sum where we divide the region in 5 parts in the r direction and 6 parts in the theta direction. As usual, the approximation gets better when we subdivide the region in smaller polar rectangles. The volume of each bar is the product of the height, which is the function value at the chosen point, with the area of the small polar rectangle. Now something peculiar happens. The area of such a small polar rectangle is not equal for each small polar rectangle. The further away they are from the origin, the larger this area becomes. So how can we compute the area of such a small polar rectangle? Let's assume the difference in radius within this polar rectangle is dr and the difference in angle is d theta. Then the arc length of the curved side is given by r d theta. As such, the area is more or less the same as the area of a regular rectangle with sides dr and r d theta, which then becomes r dr d theta. Indeed, this area becomes bigger if the polar rectangle is further away from the origin. So, suppose we have a continuous function f and a polar rectangle D, with r in between a and b and theta in between alpha and beta. We find that if we want to express the double integral of f over d in polar coordinates, we should replace x by r cosine theta, y by r sine theta, and dA by r times dr d theta. This means that an extra factor r appears in the integrand. This extra factor r is called the Jacobian, and it is essential that you do not forget it in your computations. The resulting integral is now an iterated integral, which you can proceed to compute as you are used to. Note that the constants a and b, which we defined as the lower and the upper bound for r in the definition of the region D, now appear as the limits of the inner integral over r. Similarly, alpha and beta, the lower and upper bounds for theta, appear as the limits of the outer integral over theta. There are two technicalities that you need to keep in mind. The first is that a, the lower bound for the variable r, should always be positive, as r represents a distance. The second technicality is that the limits of theta should not be more than 2 pi apart from each other, since otherwise you integrate over the full circle several times extra. You simply avoid this issue by consistently choosing theta in one of the standard intervals minus pi to pi or 0 to 2 pi. We can use polar coordinates to describe regions that are more general than polar rectangles. Usually, these are regions where the radius r is bounded below by some function h1 of theta and bounded above by some function h2 of theta. Theta is then bounded between the fixed numbers alpha and beta. For such a region, you can express a double integral as an iterated integral, where the functions h1 and h2 take the role of the limits in the inner integral. Again, it is essential that you do not forget the extra factor r here. To close off our treatment of double integrals, let's do two examples. First, consider the region D, which you see on the screen. This is a polar rectangle where r is in between 0 and 1 and theta is in between pi over 2 and pi. Suppose we want to integrate the function x squared plus y squared plus 2y over x squared plus y squared over this region. In regular Cartesian coordinates, it is very hard to compute this double integral, as both the description of the region and the function are rather complicated. So let's try instead to switch to polar coordinates. This means that we should plug in the polar coordinates for x and y and multiply the entire function by the extra factor r. Remembering that sine squared plus cosine squared equals 1, we can greatly simplify this function and end up with the function r plus 2 sine of theta. So both the description of the region and the function simplify significantly when switching to polar coordinates. We are left with an iterated integral which we can compute as usual. As our final example, suppose we want to compute the area of the rose petal-like figure you see on the screen. In polar coordinates, the boundary of this region is given by the equation r equals cosine of 2 theta, and theta takes values in between minus pi over 4 and pi over 4. Remember that, in general, the area of a region can be expressed as the double integral over this region of the constant function 1. So in order to compute the area of the rose petal, we switch to polar coordinates. The new integrand becomes the function 1 times r, which is simply r. Notice that the limits in the inner integral over r are functions of theta. This iterated integral can be computed using regular integration techniques, and we find that the area of the rose petal equals pi over 8. That's it for the topic of double integrals. Do not forget to practice the material and see you next time.